How can a so-called powerless booster locomotive make a railroad stronger? Every day in Sandersville, Georgia, dozens of covered hoppers loaded with raw kaolin clay line up in the yard. Each car carries close to 100 tons of this fine, dense mineral, enough to fill a small swimming pool with pure white powder. In a typical year, the railroad moves between 150,000 and 200,000 tons of kaolin, most of it bound for paper mills, ceramics plants, and pigment factories across the Southeast. The scale is easy to overlook, but the numbers add up quickly. A single cut of 6 to 8 cars can weigh over 600 tons, and crews repeat this process shift after shift. In this world, time is measured not just in hours, but in seconds. The value of kaolin comes from volume, not price per ton. Margins are thin, and every extra minute a loaded car sits in the yard waiting to move is money lost, both for the railroad and for the customers downstream. Many of those customers run just-in-time production lines, where a delay of even 10 minutes can force them to switch to trucks or pay late delivery penalties. The pressure to keep cars moving is relentless, and any tool that can shave seconds off a switching cycle becomes a quiet advantage. But there is a hidden constraint behind these numbers. When a switching crew lines up a cut of kaolin hoppers and prepares to start from a dead stop, the challenge is not a lack of horsepower, it is the fight for traction. How much of the locomotive's force can actually be delivered to the rails without the wheels slipping? Before diving into the physics that governs this invisible limit, it is worth pausing on the stakes. In Sandersville, the difference between a smooth start and a slipped wheel is measured in seconds, but those seconds ripple out through the entire supply chain. Steel wheels on steel rails seem unstoppable, yet their grip on the track is surprisingly fragile. The core physics comes down to a single formula: F equals mu times N. Here, mu is the coefficient of adhesion, the measure of how sticky steel is against steel, and N is the weight pressing down on the driven axles. On clean, dry rail, mu is usually between 0.3 and 0.45. That means for every ton of weight on a powered axle, only about a third to nearly half a ton of force can be used to pull the train before the wheels start to spin. But when rails are slick with rain, leaves, or a fine layer of kaolin dust, mu can drop as low as 0.15. Suddenly, only a fraction of the available weight translates into usable tractive effort. If you have ever tried to push a heavy cart across a polished floor, you know muscle alone is not enough. The cart just skids if your shoes cannot grip. Locomotives face the same problem, command too much torque and the wheels slip. When that happens, the pulling force collapses almost instantly, and all the horsepower in the world cannot move the train until grip is restored. For Sandersville's switching crews, this is not just theory. A typical mother locomotive, like an MP15DC, might have 4 powered axles, each carrying about 37.5 tons. On dry rail, that is enough for a starting pull of around 45,000 pounds. But at a slug, ballasted to put another 80 tons on 2 more powered axles, and the total usable tractive effort jumps by 20% or more, even though the engine's output stays the same. The secret is not more power, but more grip, precisely distributed. This is why in the world of heavy switching, the limiting factor is not the size of the engine, but the physics of adhesion and the ever-present risk of wheel slip. The real engineering challenge is to keep every pound of available force working for you, not fighting against the rails. A slug looks like any other locomotive, but under the hood the difference is fundamental. There is no diesel engine, no generator, and no radiator fans humming inside. Instead, the heart of a slug is its heavy steel frame, often a recycled road switcher like Sandersville's number 90, which started life as a GE-23B in 1963. During conversion, the prime mover is removed, leaving the original traction motors on each axle. Into the empty engine bay goes a dense mix of concrete and steel ballast. The result is a unit that tips the scales at 120 tons, with about 80 tons pressing down directly on its powered axles. When a slug is coupled to a mother locomotive, typically an MP15 DC switcher in Sandersville, the two are joined by a multiple unit cable. This thick bundle carries 480 volts of direct current from the mother's generator straight to the slug's traction motors. The slug draws up to 1,200 amps during a heavy start, pulling roughly 30% of the mother's total output. There is no new fuel burned, just a smarter division of available electricity. The key is how this added weight changes the numbers in the adhesion equation. With more tons pressing down on more driven axles, the normal force, called N, increases. That directly raises the maximum tractive effort. F equals the coefficient of adhesion times N before the wheels slip. Field measurements show that the mother-slug pair can generate 35 kilonewtons more pulling force than the locomotive alone, a boost of nearly 20%. For the crew in the cab, the difference is immediate. Longer cuts of loaded kaolin cars start rolling with less risk of spin, and the amperage gauge stays in the safe zone. On camera, a veteran Sandersville engineer describes the process as putting every pound to work. He points out that in practice, the slug's ballast is carefully distributed above the powered trucks. This ensures that every bit of added weight translates into real grip, not wasted mass. The engineer checks the amperage meter during each start, confirming that the slug is drawing its share and that the current stays just below the slip threshold. It's a routine, but one grounded in physics and in the daily pressure to keep the kaolin moving without interruption. Imagine two people trying to move a heavy sofa across a slick tile floor. No matter how strong they are, if their shoes cannot grip, the sofa barely budges. Their effort just slides away. That is the reality Sandersville's crews face every time they start a loaded cut of kaolin hoppers. In the cab, the engineer knows muscle, horsepower, does not matter if the wheels cannot hold the rail. The real contest is for traction. To make this concrete, the yard ran a simple test. With only the mother locomotive, a 6-car cut took just over 3 minutes to start and clear the lead. When the slug was coupled in, the same move finished nearly half a minute faster. On paper, it is 4 seconds saved per car, 30 seconds per cut. But in the rhythm of a busy yard, that is a small revolution. Over a shift, with 18 to 24 starts, the time saved adds up to nearly 10 minutes. Those minutes ripple outward, tightening schedules all the way to the Tennille interchange. A veteran conductor puts it plainly. With the slug, you do not have to baby the throttle. You just ease it open and let the amps come up. The wheels bite, the cut moves, and you are on to the next job. Protocol calls for a quick check on the amperage gauge. If the needle stays steady, the start is solid, and the dispatcher can line up the next move without delay. The numbers tell their own story. Since making the slug standard, on-time departures from Sandersville have climbed from 82 to 94%. For kaolin customers running just-in-time lines, those few extra minutes mean fewer production stoppages and less risk of a costly switch to trucking. In this system, grip beats muscle every time, and a locomotive without an engine quietly keeps the whole supply chain on track. On the edge of downtown Sandersville, the arrival of longer, heavier trains brought new challenges for local traffic. In 2021, city engineers responded by redesigning the Main Street rail crossing into a roundabout-style intersection. The new layout replaced traditional gates with low-profile barriers, flashing LED lights, and a raised central island that forces drivers to slow to 15 miles per hour. Pedestrian walkways now guide foot traffic across clearly marked paths. Within a year, traffic studies reported a 47% drop in vehicle-train conflicts and a 30% reduction in vehicle speeds through the crossing. Nearly all pedestrians began using the designated route. These changes didn't just improve safety. They showed how a small town can adapt its streets to fit the shifting patterns of rail commerce, balancing growth with public well-being. The proposed Hanson Spur has become a lightning rod for debate in Washington County. On paper, a 4.5-mile rail extension promises to shift up to 15,000 carloads a year from trucks to rail, cutting an estimated 3,200 tons of carbon dioxide annually and generating between $1.2 and $1.5 million in new revenue. County planners argue these numbers justify the project under Georgia Statute Section 44-5-41, which allows railroads to acquire land for public use. They point to reduced highway wear, lower emissions, and economic growth as benefits that ripple through the region. But landowners along the planned route see the spur differently. Many argue that the track would carve through productive farmland, depress property values, and that compensation offers fall short of market rates. In early 2024, a group of residents filed suit, challenging both the process and the necessity of the taking. The resulting standoff has made the Hanson Spur not just a question of logistics, but a test of how communities weigh the promise of economic gain against the cost to individual rights. Right now, railroads like Sandersville show that real progress comes from working with physical limits, not just overpowering them. In a world obsessed with horsepower, it is grip, the quiet science of adhesion, that moves the heavy loads. Sometimes, smarter solutions are hiding in plain sight. Thanks for watching.